Welcome to a full breakdown on the Bitcoin blockchain and how it works. Now, this is not a video about if you should buy Bitcoin or what price it's going to. This is just a look at the nuts and bolts so that you can make an informed decision on your own about this technology and what it might be useful for. And the analogy that I like to use is that a car is very complicated when you look at the whole thing. When you actually break it down into the small components and the springs and the nuts and bolts, no one part of it is all that difficult to understand. And what I'm going to be doing with the Bitcoin blockchain is breaking down the individual parts of it and then showing you how they work together. Starting with this SHA-256 hash. This is the most important part of the entire process and what makes Bitcoin possible. It stands for Secure Hashing Algorithm. And what a hashing algorithm does is that it takes any input, let's say someone's name, and it gives a specific output. Now, this output might at first look like a blend of numbers and letters, but it is actually a hexadecimal number, where each position can either be 0 through 9 or A, B, C, D, E, F to represent the numbers above 10. And so this is actually just a number where each position can be up to 16 different characters. So for each piece of data input, you'll get a unique hash that can be recreated by putting in that same data. So you'll notice that if I delete the name here and then put it back in, I'll get that same hash that starts with the D389 every time. So I can't tell what data was input based off of what the hash says, but for a specific data input, I will get the same hash every time. So here's an example of how that works. You've got different inputs leading to an output number, and it is possible for the same input to have what's called a collision and to result in the same output number. But the important thing to know about how these functions work is that they can't be reversed. You can't reach into a smoothie and then pull a blueberry back out of it after it's blended. That's the point of this hashing function happening in the middle, is that it's one way, which is why we represent it with an arrow here. So for each given hashing function, I will get a hash output, a hexadecimal number that is specific to what that input was earlier. So now using that in a block and making it a little more complicated, but still nothing hard to understand, we've got the block number, which is also referred to as the block height in Bitcoin. We have what's called a number only used once, which is actually what the miners are changing around, and I'll show you how that works in a second. And then we've got the same data. So all that we've really done is broke this data field up into a couple of other formatted fields so that we can do useful stuff with them. So let's say that I want to put in that same name, and I want to get a hash that actually starts with 4 zeros. This is what's called a target difficulty. This block is not considered valid by the blockchain or by whatever program is using this until that hash starts with a certain number of leading zeros. In this case, it will be 4 leading zeros. So when I hit mine, what this block is going to do is guess a different nonce that will actually make it so that the resulting hash output starts with those 4 zeros. So I hit that and it thinks and it gives me a specific nonce. Now the way that this was first used was by a guy named Adam Back when he invented Hashcash. And the idea was that if I wanted to send a message to the government, I could send that message to the government, but I would have to accompany that message with a nonce that works out to create a hash that satisfies that block condition. And the reason for doing this is as a legitimate sender of that message, it's not a problem for me to spend a couple of seconds of computational energy, 1 penny worth of electricity, to actually do the math to send that message, but it prevents people from spamming and from sending thousands of messages and possibly overloading that system because each message actually requires a little bit of work to be done in order to validate that message. So originally this was a DDoS countermeasure, so a way to prevent people from a distributed denial of service attack where they're effectively just overwhelming a messaging server. This is a way to make it so that the sender actually has to do a little bit of work and it prevents them from doing that spam. Now we can actually take these blocks and link them together. That's right, we have already gotten onto the big scary blockchain and what it actually means. So let's create an immutable grocery list here. So I type in some of the things that I want, and as I'm typing in the different things in these different blocks, I'll be mining it to get a resulting hash that satisfies this condition of having 4 leading zeros on it. What else do I need here? I need bread. So I've got this immutable grocery list. And the way that these things are chained together is by actually including the hash result of the previous block in the next block. So I've added in one extra field that actually refers to the hash from the previous block, and I have to include that hash from the previous block in my actual hash for this new valid block, which makes them chained together. So I can't go back and change any part of that blockchain without breaking the entire thing, because I've changed this resulting hash, and now all of a sudden none of these other hashes actually are valid outputs. So that's the way that we've created what is called an immutable ledger, a ledger which does not mutate, cannot mutate. Taking this immutable ledger, we can now distribute this immutable ledger. So, you can imagine here if I were to put in the same things, I'm making that block, and I'm mining for that different block, and we're actually distributing the results of these different blocks into multiple peers on the network as this is happening. In Bitcoin, these peers are referred to as the different nodes, and they're actually maintaining a separate copy of that block. But they'll be able to go forward and actually add to this blockchain. They can all agree on what was added to the blockchain without having to go back and check that that proof of work was valid, because they've all agreed on the state of that blockchain up to this point. I'll show you an example with these actual tokens, because this one's filled out already, and I'll link this blockchain demo site earlier. It's a really cool tool by a coder named Anders Brownworth. But here you can see we actually have a distributed blockchain where everyone's agreeing on the different information. And if I were to go back, say I was peer C and I wanted to lie about one of these transactions and actually put in an extra 0, well, now my chain is all broken and I can't go rebroadcast that to the network. Say I try to add on a new block, they'll say that new block isn't valid because you don't have a valid ongoing chain of hashes, a valid ongoing proof of work that this was done correctly. So this is what prevents people from lying to the Bitcoin network, and it's why you don't need anybody at the center of it to actually maintain that it's valid. So looking at an example of one of these chains that actually does have all of the correct hashes, I can see here that Parker pays Dallas $6.15, and this is recorded and it's immutable. But it does raise the question, did Parker ever have $6.15 to send off to Dallas? And the way that this works on Bitcoin is that initial coins come into the market through only one way. They come in when somebody solves a block. So when Satoshi solved the first blocks, he got what is called a Coinbase transaction for that specific amount. And the rest of the network, as they're changing around where that token has gone, they are referring to see if it had been established previously in a block reward and it had been carried through. So when I'm starting off this blockchain, I have this Genesis block, as it's called, where Anders figured out the correct hash. He got $100. He was able to pay himself. Well, the next block, there's nobody besides Anders that has any money to send. So the next block will be Anders sending this out to different people, and also paying getting a Coinbase transaction himself for having solved that block as well. When you hear about the halving, what is actually getting cut in half is the Coinbase transaction that's paid out to miners for solving a block. So it used to be 50, then after about 4 years that dropped to 25, then down to 12.5, and now it's at 6.25 and is actually about to change and go down to 3.125 in the coming month here. But those Coinbase transactions get cut in half, which is why eventually Bitcoin will stop being issued at all, because those Coinbase transactions will run out and it will just be coins that already exist being transacted around. So I look at Emily's transaction to Jackson over here, begs the question, well, did Emily have $10 to even send? And we can see here, in fact, she got $15 from Anders originally, and we know that he had $15 because he was issued $100 in that Coinbase transaction. So that's how they actually flow through. What we talked about so far is what mining looks like and what a hashing algorithm looks like. There's this entire separate side of Bitcoin that has to do with public and private key cryptography. And that looks quite a bit different than a hashing algorithm. This might initially look like it is a hashing algorithm, but it's a little bit different because for each private key, there's only one public key. So it's not like I can have an infinite number of private keys. In fact, if I try to add on a bunch of numbers to the back of this one, this program will actually stop me because there is not an infinite amount of public keys or private keys that can be generated. For each public key, there is one private key. An analogy that really helps make sense here is like PO boxes. You have the public key that everyone can see and they can use to send you Bitcoin, and that would be the address on the front of the box. But then you also have your own key, which is a string of numbers that you can use to prove that you actually own that transaction output and that what was sent to you is yours to control. So you can broadcast the public key and then maintain control of that private key to prove ownership of it. So when you hear about people with hardware wallets, they're not actually holding the Bitcoin on their specific device, be it a cold card or a Jade or whatever other device. What they're holding on there is a key, and the Bitcoin transactions are actually recorded on the blockchain, and they're able to use that key to prove that they own a certain transaction. So moving forward with how that actually looks, I'm going to do what's called a signature here. So say that I have my specific message, I'm sending $10 to Karen, and I control this private key. Well, now using the message that I want to send and combining it with that private key, I can sign and create a unique message signature. Now, this message times my private key will create the same signature, and this message times the public key that will actually be on the blockchain will create the same signature, which is how people can use this to verify each other. So in this verification step, I put out this same message, I have the public key associated with it, and I have broadcast this message out with its own signature, basically signing in this block and saying that this one is valid. And anybody in the network can check that that block was in fact valid and that that message is what I wanted it to be, because they have access to the public key that they can use to check it against the message. And they know that the person who made this message and who signed this message must have control of the private key, because there's no way that they would have been able to get that signature otherwise. So if I wanted to change up one part of the message, all of a sudden that block won't verify. If I didn't have the correct public key, all of a sudden that block won't verify. So that's in essence how the public-private key cryptography actually works in this instance. Now, you can imagine it's the same thing as that previous example where we've just broken up the message into a couple of formatted fields so that we're able to use them. And this is starting to really look like what actual Bitcoin looks like. So instead of having people's names on here, Bitcoin is pseudonymous. So there are public keys and people can prove their ownership of them using private keys, which means you don't need a bank account, no one needs to check who you are, there's no identity associated with any of this. You're able to prove ownership of that public key because you have the private key. So say that I want to sign this message, I've signed it, created a message signature, and now anybody else on the network can verify using my public key and combining it with the message that whoever put out that message and wrote that signature actually did control those private keys and had the key to that PO box, had the key to that wallet over on that public blockchain that they're now able to send out of. And kind of wrapping up everything that we've talked together, we now finally get to a blockchain that looks somewhat similar to how the actual Bitcoin blockchain works. So we have a Coinbase transaction that has been created, and we know that these all have valid nonces. All of those nonces have been mined. These are all valid blocks because all of the hashes satisfy that hash requirement of starting with a certain amount of zeros. So now this Coinbase transaction is going out to this public key. So everybody that's looking at this knows that that public key got a Coinbase transaction, solved a block, and now this key controls $100 worth of funds. Now, the second example, this key is actually going to be sending them out to different public keys. And to prove that the owner of this public key actually wanted that to happen, all of these messages include this message signature, which everyone else can use to verify that that person did indeed control the private keys for that message. And now continuing on, we can see this public key is now trying to send some funds over to this public key. And we can see that this public key did indeed have those funds because they got them in this earlier transaction. And we know that the person sending those coins to them had access to that because they were paid out $100 in a Coinbase transaction right there. So again, none of these parts are all too complicated to understand individually when you look at them, but when you pair it all up together, you create this blockchain that anybody can participate in, It's very hard to lie to. You actually can't lie to it unless you have more computers than that network has, which currently Bitcoin is the most powerful computer network on Earth by a really wide margin. So you have this immutable public ledger that you can use to create this monetary system around rules, and not have any central entity have to maintain that and verify that it's true. Every node on the network is able to do that in a decentralized way. So there you have it, a full breakdown on the Bitcoin blockchain and how it works. Thank you very much.